Hello, my name is Yugjeet Grewal, and today I will be presenting our research project called Online Radiation Experiment on Gamma Ray Absorption from an Early Quack Device. My contributors for this project include Ruben Reyes and Raul Reynoso, who are my peers and were undergraduate students at Fresno State, Michael Walkup, undergraduate student at University of Oklahoma, and Dr. John Walkup, who was our advisor for this project. We know that radioactive materials are hazardous and that it can be dangerous to put high school students or students taking introductory physics courses in college next to radioactive materials for them to conduct any kind of experiments. We also know that the COVID-19 pandemic has made life difficult in many ways, and we experienced this when we had to move our research project from in person to everything being online. We were able to complete our project, but we discovered that it wasn't just that. It was a safer way for us to conduct radiation experiments at a safe distance. I present a safe way for high school or college students taking introductory physics courses for them to conduct radiation experiments where only the instructor is the one who actually comes in physical contact with the radioactive source. We took a student-centered approach for this project. By that, I mean that my peers and I designed the experiment and our instructor set it up for us in his lab room on campus. And that was because of the COVID-19 restrictions. We used a Geiger-Muller tube to measure radiation levels. However, the instrument or the apparatus itself, the Geiger-Muller counter itself, has a significant drawback. It has a gauge with a needle on it, but the needle moves back and forth very quickly. So it's almost impossible to take accurate measurements over longer period of time, for example, over 10 minutes. We used an audio editing software to overcome this problem. So we came up with a solution where we would record the audio of the clicks produced by the Geiger counter. We would put it in Audacity, which is an audio editing software, and we would initially manually count the number of spikes which correspond to each click produced by the Geiger counter. But then one of the contributors created this Python code. He edited in a Python code that he found online, and we used that Python code to count the number of clicks for us. For our radiation source, we used a Radium Ore Revigator, which is a Quack medical device from the 1920s. It's been lined with radioactive materials on the inside, usually radium 226, which has a very long half-life of around 1600 years. Why the Revigator, you may ask? Because it has historical significance. And our instructor had access to a Revigator. So the first one was made in 1920s by R.W. Thomas, who was a stock salesman. He marketed it as a cure for all. So he would ask people to put water in it overnight and then drink that water in the morning in the false belief that it will cure all diseases that they might have. By the year 1930, the deaths of radium dial painters, also known as radium girls, were in the news. And hence no units were sold after 1930. The experimental setup. So our goal was to find the half value layer of steel for radium 226 gamma rays. By half value layer, we mean, let's say that we begin with an initial level of radiation. What's the thickness of steel that will reduce that initial level into half? The Geiger-Muller probe, which is this, is positioned right above the revigator. We stack sheets of steel in increments of 2 on top of the revigator, and then the Geiger counter, it measures the level of radiation able to pass through this combination of sheets. It produces a click each time a radioactive particle enters the device, and that's what we record in our audio files. Each spike is a click. So we positioned a microphone next to the Geiger counter speaker. It transmits audio through Zoom to the students. Each student records their own clicks using Audacity, which is a free app available for all operating systems. And then the spikes are counted using the Python code, which this is a picture of a section of the Python code. And if you're interested in the code, please email me. We also accounted for the background radiation levels. This is a video of our setup. So it's from initial trials. That's the probe, the shielding material, steel plates, and the revigator. We were using a microphone app to amplify. So this is feeding audio into a Bluetooth speaker, which amplifies the clicks, but it's not always required. The speaker feeding audio into the computer, which is on a Zoom call, and we, the students, are receiving that audio, which we're recording in Audacity, the free audio editing software that I mentioned earlier. And you can hear the clicks in the background. So we plotted, we got the number of clicks in the 10-minute period that we used for each level of thickness. We recorded our data for 10 minutes for each thickness level, and we found the average number of clicks per minute and plotted it against the thickness of steel. Then we used Excel to give us an exponential function because we know that this relation is exponential. And we used the intensity equation. So this is intensity equals initial intensity e to the negative lambda, which is the decay constant, x, which is the absorber thickness. And we're interested in half of the initial intensity. We take natural log of this equation, and we get x naught, which is our thickness, is equal to natural log of 2 divided by the decay constant that this data gives us. We found the half value layer to be 15.4 millimeters, which agrees with the previously cited values. So this project represents a course-based undergraduate research project, and it's an interactive way for students to learn about a topic. We think that high school and college students taking introductory physics courses can participate in meaningful nuclear physics research by conducting these kind of experiments online at a safe distance where only the instructor is the one who comes in contact with the radioactive material, and they are much better prepared to be near that radioactive material than a high school student is. And here the students can design their own experiments, and then the instructor can set it up for them, and then they record all of the data over Zoom, and then they do their data analyses and come up with conclusions based on their data. That's the works cited page. And contact information, mine and Dr. Walkup's. And that's all I have for you. Thank you.